Okay, I'm gonna go through question 21 in the latest practice test that I handed out, but it's honestly a pretty convoluted question, something you probably wouldn't see, but it's helpful in understanding how bridge circuits work, and ultimately it is somewhat of a good question to know, a roundabout question to know. Either way, let's go through it. All right. So the first thing we need to know is exactly what a Wheatstone bridge circuit is trying to accomplish. Here we have our traditional circuit. We have a galvanometer in the middle. It's in between two resistors, which are two sets of resistors that are in parallel with one another. And it's looking to find zero potential difference or zero voltage between this point here and this point here. And it's a measuring device with the rheostat on one of the resistors here. And as the rheostat as you turn the knob, you're changing the resistance of R3. And as you change the knob, that's going to change the ratio, the relationship between R1 and R3. And it's going to work through different ratios. And as soon as you turn that knob and that ratio matches R2 and Rx, well, that's going to balance the galvanometer here, and there's going to be 0 volts there. So that's what we're trying to do. Now, R1, R2 would be fixed values. We would know what those resistive values are. R3 would be a rheostat, and that's going to have a range of resistances starting at 0, or for simplicity's sake, we'll say 1 ohm, all the way up to its maximum resistance. And Rx would be the mystery resistance that we're trying to solve for. Okay. Now, again, if R1 and R3, if that ratio matches R2 and Rx, and we know what R1 is, and we know what R2 is, and we are able to know now what R3 is, then we would be able to solve for Rx. Okay, so that's how a Wheatstone bridge works. Now, in this particular question, we have a set of values. We've got 4 different options, different sets of values for each of those resistors. And basically, the way that I solved it was just plug in the resistances that match our variables and see if you could get a ratio that would work. So a ratio between R1 and R3 that was able to be the same as R2 and Rx. All right. So in this particular question, then we're given the value of Rx. We know that it is 250 ohms. And we want to know if the other resistors are appropriate values to actually measure and be able to figure out that that would be 250 ohms. Hopefully, as I do this here, it's going to make more sense. But let's go through A here. So A, if I plug in the values, I got 60 ohms is equal to R2 is 150. Our maximum resistance of a rheostat here is 75. Okay, so a 75 ohm rheostat means that at the max setting, you're going to see 75 ohms. At the lowest setting, you're going to see essentially 1 ohm. So we're going to put it 1 to 75 ohms. So really, it would be 0 to 75, but again, for simplicity's sake, we'll say 1. And we know that Rx is 250. Okay. So first of all, I want to know what my ratio here equals on R2 and Rx. So this here would equal, if I were to divide 150 into 250, 0.6. All right. Now, if I were to solve for 60 ohms and on the max setting of 75, that's going to give me a value, a ratio of 0.8. Okay, so that would be 60 over 75 gives me 0.8. And you'll notice that's too high for the 0.6, 150, and 250. But the beauty of a rheostat is that you can adjust the resistance. So as we go down, if we go to our minimum resistance, 1 ohm, well, 60 over 1 would give us 60. So we have a range of ratios from 60 to 0.8. All right, that's our range of ratios. And you'll notice that 0.6 does not fit inside that range. And so therefore, you wouldn't be able to use this configuration of resistors in a rheostat to balance that circuit. So that's essentially what the question is asking. Can you use these particular resistors given in each of these options here, A, B, C, and D, to be able to balance that circuit with the Rx of 250 ohms? So for A, the answer is no, again, because 0.6 does not fit in the range of 60 to 0.8. It is too small. All right, so let's go through B now. So this time we have 100 ohms for R1. R2 is 50. Our rheostat is anywhere from 1 to 400. And Rx again is 250. Okay, so let's solve the ratio here. 50 divided by 250 would give us 0.2. If we were solving that fraction, 0.2. Now let's solve here. 100 divided by 400 would give us 0.25. Okay, so that's the minimum that it can give us. And if we were to change that rheostat all the way to 1, well, ultimately we could get a ratio of 100. So anywhere from 100 to 0.25 on R1 and a rheostat, R3. But again, this 0.2 does not fit inside that range, and therefore we would not be able to balance the circuit and determine that the Rx would in fact be 250 ohms. Okay, so trial and error. We'll try letter C. So we got 1,000 ohms. R2 is 500 ohms. The rheostat is anywhere from 1 to 1,000. And we know that this is, Rx is 250 ohms. Okay. So the ratio here is, if we were to solve that, is 2. 500 divided by 250 is 2. And 1,000 divided by 1,000, so at the minimum range, is 1. This is looking good. And if we were to dial back that rheostat all the way to 1 ohm, we could say our maximum is 1,000. So we could read anywhere from 1,000, a ratio of 1,000 to 1, all the way to 1. And indeed, our ratio over here, 500 over 250, does fit within that range of 1,000 to 1. So we could use this combination of resistors and a rheostat to be able to balance this circuit with the 250 ohm resistor as our mystery resistor. So the answer here would be C. And if you were to try to figure out D, you would again determine that the ratios the ratio of R2 and Rx does not fit inside the range of ratios of R1 and R3. Okay, so hopefully that helps. Again, a bit of a convoluted question, but we can go over it again when we're back in class.